What happens when a comet appears to take a breath? 3E Atlas, an explorer from a distant star system, is expelling 40 kilograms of water each second into the icy emptiness, way beyond the sun's reach where such actions seem out of place. Scientists murmur, it's behaving like it's alive. Yet this comet's tail goes much deeper. Peculiar nickel lacking iron, cyanide trailing in its wake, and hints of origins stretching billions of years before our solar system formed. In the meantime, beyond this cosmic outsider, amateur astronomers uncover the biggest unusual radio circles discovered so far. Mercury's passage and alignments coincide with intriguing timing across October's night sky, sparking speculation about connections to 3E Atlas, while Blue Origin's October launch stirs up more puzzles than solutions. Did it truly occur? Stick around to the finish as we tackle these eerie enigmas in our debut multi-narrative style, designed to keep our overnight audience clued in on the latest celestial happenings overhead. If these riddles grip you like they do me, remember to like and subscribe to catch every fresh reveal. With events unfolding live, chime in below about your location, local time, and if you think we're hearing the whole story on these game-changing finds. To build this group stronger, spread this clip on X, Facebook, Reddit, or your personal chats. You make it possible for us to pursue tales like this. So, thanks for supporting us. Part 1. The Unbelievable Emission. Imagine drifting through space's frigid hush, over 3 times Earth's distance from the sun. Here, solar rays fade to a murmur. Frost remains solid. Comets lie inactive. All is at rest. Then it appears. A comet unleashing water into the vacuum, spewing 40 kilograms of it outward every second. Not a drip, but a torrent. Liquid surging from an icy boulder where no flow ought to exist. Meet 3E Atlas, an interstellar wanderer that entered our solar system from afar, bringing laws from another stellar domain. And those laws clash with what we know. The initial hint arrived via SWIFT, a telescope built to detect gamma-ray flares. In early 2025, SWIFT directed its ultraviolet gaze at 3E Atlas and detected something inconceivable. A ring of hydroxyl molecules encircling the comet. Hydroxyl, or OH, forms when solar radiation splits water apart. It's the remnant of water breaking down. Spotting OH signals recent water presence, and SWIFT observed plenty. The figures are jaw-dropping. At 3.51 astronomical units from the Sun, 3I Atlas emitted 1.35 times 10 to the power of 27 water molecules per second. That's 40 kilograms every second. Non-stop. To put it in perspective, it's akin to releasing a compact vehicle's volume of water into the cosmos each minute, in a region where local comets scarcely stir. Comets from our system avoid this. Not at this range. So remote from the sun, they chill, hibernate, nearly lifeless. Water ice requires warmth to vaporize straight from solid to gas, skipping the liquid phase. Yet solar power proves insufficient out there to fuel such vigor. Our comets hold off until nearer the sun to rouse and release gases and particles. 3 Atlas ignored that pattern. Recall Oumuamua, the inaugural verified interstellar guest. That object stayed arid, no moisture, no emissions, merely a spinning stone racing past. Quiet. Next was 2I/Borisov, the follow-up interstellar comet. Borisov showed activity, yes, but mirrored our own comets perfectly. It stuck to the playbook. Reliable. Unremarkable in the most reassuring sense. 3 Atlas defies both. It pulses with life improbably. It blasts water where quietude should dominate. And the puzzle tormenting every observer trained on it boils down to one word. Why? What force could propel this? Perhaps an unfamiliar frost that evaporates at chillier temps than expected? Does the core retain heat from its ancient formation? Might odd spinning concentrate light on concealed volatile stores? Or could internal reactions unfold that we've never witnessed? Watermarks only the start. 3 Atlas also releases cyanide, nickel, carbon dioxide at baffling levels. Fresh scans deepen the enigma. Every spectral signature in the readings poses yet another query. This goes beyond quirky conduct. This comet functions by alien physics. Laws forged in a foreign system amid unique environments and reactions. Now in our midst, it offers prime viewing of those workings. Astronomers can't stop pondering this unprecedented sight. The real puzzle keeping experts awake is what it means if 3 Atlas behaves in ways our own comets never do. Where exactly did it originate? What sort of stellar environment produces such unusual icy bodies? How were conditions in its ancient protoplanetary disk billions of years back? And the most intriguing question of all, is this visitor simply an outlier, or does it bring tidings of the universe's vast diversity? Telescopes worldwide capable of detecting it are locked on target. From spectral analysis and light measurements to polarization studies, we're deploying every instrument available. After all, 3 Atlas goes beyond mere intrigue. It's a portal, a fissure in our cosmic knowledge. Peering through that fissure could reveal wonders we never imagined. Part 2. Nickel on its own, sans iron. Typically, comets adhere to established norms. As they warm sufficiently, metals begin vaporizing from their exteriors. Iron and nickel emerge side by side, inseparable companions that always show up together. Spot one, and the other is sure to follow. This is a reliable principle of the cosmos we've long trusted. Yet, 3 Atlas defies the script entirely. The Very Large Telescope in Chile directed its spectrometer toward it, an uncovered and baffling result. Nickel spectral lines glowed vividly in the data, intense, undeniable, impossible to overlook. Iron, meanwhile, was either missing or so faint it scarcely appeared. Nickel isolated from iron. It's akin to discovering vapor without a blaze, or tracks without any creature making them. In our solar system, such a scenario is unheard of. When a comet warms to the point of metal release, iron and nickel emerge in consistent proportions, bound within identical mineral formations. They originate from parallel formation mechanisms. They vaporize at comparable heat levels. Their chemical links ensure they remain linked. Evidently, 3 Atlas arose in a realm governed by alternate principles. At roughly 2.8 astronomical units from the Sun, observers detected nickel streaming from the comet at around 5G/s. That figure might seem modest at first, but consider its ongoing, moment by moment, with no trace of iron. This isn't an error, it's a clear signature. It's the comet revealing core truths about its makeup. Various theories have surfaced, and they're all complex. One suggestion points to chemical separation. Perhaps in 3 Atlas's formative setting, nickel integrated into easily vaporized volatile substances, whereas iron embedded in heat-resistant minerals requiring extreme temperatures to release. Imagine nickel tagging along with fleeting ices, leaving iron stranded in durable rocky particles, thus causing the split we observe. A different hypothesis centers on organometallic structures. Here on Earth, we encounter entities like nickel carbonyl, where nickel atoms attach to carbon monoxide. Such materials are highly volatile, subliming at modest warmth. If 3 Atlas originated amid abundant carbon monoxide and organic materials, nickel could have been ensnared in these formations. Solar radiation would then break them down, freeing pure nickel into the surrounding gas cloud, while iron stays confined in solid fragments. Space weathering offers yet another angle. Interstellar travelers endure relentless pummeling from cosmic rays and UV light over eons. This prolonged exposure can warp surface compositions in bizarre fashions. Radiation might forge nickel-enriched outer layers, while iron sinks deeper or undergoes chemical shifts. The nickel we detect could be merely a superficial coating, a battered exterior that doesn't mirror the comet's inner substance. Or, and this scenario thrills most, 3 Atlas might hail from a star system with truly distinct elemental ratios. Not every star shares identical chemistry. Ancient ones, those in varied galactic zones, or those born from supernova-fueled gas with unique enrichments all boast subtle variations in their mixes. Perhaps 3 Atlas's home turf had nickel far more plentiful compared to iron than in our local patch. Its parent star could have been compositionally peculiar, imprinting that anomaly into each atom of this wanderer. Caution is essential, though. Spectral work is challenging. Picking out dim lines amid glaring backdrops demands precision. Detection limits exist for a reason. Iron could lurk just beyond our current sensitivity. Its signals might overlap with other features in the spectrum. We could be scanning improper bands. As the comet approaches the Sun more closely and intensifies in heat, iron may finally emerge. That outcome would restore some comfort, affirming the universe's familiar logic. But suppose it doesn't? Imagine 3 Atlas reaches perihelion, its nearest solar approach, and iron remains absent. What if the nickel-to-iron balance persists in total reversal against all prior observations? That discovery would upend everything. It would reveal that planetary systems astronomers are glued to Comet 3I/Atlas because it can generate comets featuring metallic compositions so alien to our own that they force a total rethink of our theories. That's precisely why experts are monitoring this interstellar visitor with such intensity. Each viewing serves as an experiment. Every spectral analysis offers an opportunity to either validate what we know or dismantle it entirely. At the moment, 3I/Atlas is leaning heavily toward the dismantling side. Part 3. A comet that activates unexpectedly. Typically, comets should grow brighter steadily as they near the sun. The science behind it is simple. Increased solar radiation leads to greater warmth, which triggers more evaporation of ices, releasing additional vapor and particles. The progression ought to be even, foreseeable, and rather routine. But 3I/Atlas clearly ignored that guideline. Those tracking 3I/Atlas spotted an odd change in its hue. Initially, the object appeared fairly neutral, perhaps with a faint red tint, common among far-off frozen objects. Yet as it drew nearer to the sun, it began shifting to green. This wasn't a faint change. It was a striking, ghostly green that stood out clearly in images. That coloration arises from 2 elements, cyanide compounds and nickel atoms. Each glows brightly in the green wavelengths, and their output surged sharply as the comet heated up. The rise in luminosity wasn't steady or gradual. It was exponential, with the spectral lines growing stronger than basic orbital mechanics would suggest. As a body gets closer to the sun, solar energy quadruples for every halving of distance. That's the inverse square principle, fundamental stuff. However, 3I/Atlas's outputs were escalating even beyond that rate. It seemed like some barrier was breaking. A fresh mechanism was engaging. Scientists refer to this as switch-on activity. Picture a critical heat point. Under that level, certain ices remain frozen, sealed tight, inactive. Then, once the comet surpasses it, that ice begins to vaporize rapidly. Gas output spikes. Fresh spectral signatures emerge. It's akin to toggling a light. Off one instant, fully lit the next. And if sufficient reserves exist, it can spiral out of control. 3I/Atlas appears to possess several such triggers. Water vapor activated earliest, around 3.5 Australian dollars, which is unusual in itself. Next followed the cyanide and nickel, producing that intense green glow as temperatures climbed. Every signal points to a separate stockpile of volatiles being accessed, each chemical zone hitting its ignition point. One theory to account for this posits enlarged frozen particles in the surrounding haze. Rather than all action occurring on the core's surface, consider tiny ice chunks ejected from the nucleus by venting gases. These particles drift outward, remaining chilly and intact. But as they travel, they absorb escalating sunlight. Soon, each one hits its sublimation limit and starts releasing gas. This spreads the gas production across a widespread haze, not solely from the heart, but from an encircling swarm of frosty bits. Such a setup could justify the explosive luminosity surge and the abrupt emergence of novel spectral features. Alternatively, consider heat-induced splitting. Comets are essentially grimy ice balls, blends of frozen water and minerals. When sections expand from warming while others contract in the chill, internal pressures mount. Inevitably, fractures form. A split in the ice can uncover protected materials that were shielded before. Abruptly, additional areas begin evaporating, fresh gases burst free. The comet undergoes a flare-up. For 3I/Atlas, this heating might be causing it to fissure, unveiling successive strata of encased compounds. Beyond that, think of the unusual frozen substances. Water ice turns to gas at a specific heat. Carbon monoxide ice does so at far lower temps. Carbon dioxide falls midway. If 3I/Atlas is structured in layers, like an onion with varied ices in distinct zones or depths, warming would unleash them sequentially, starting with the most fragile ones, moving to standard volatiles, and ending with the toughest holdouts. Each stratum reveals itself progressively, like pages turning in a narrative. This isn't wholly unfamiliar. Comets within our system have pulled off bizarre feats. Certain ones flare dramatically, boosting brightness tenfold or beyond in hours. Others fragment nearing the sun, as heat stresses exceed their cohesion. Some linger inactive until deep into their solar grays, then burst into frenzy. Yet 3I/Atlas follows a timeline that defies our norms. It's active at ranges where it should be inert. It's igniting in patterns that almost seem intentional, and the suspense is mounting. As 3I/Atlas presses onward, might additional triggers activate? Could unforeseen spectral lines surface? Unexpected compounds? Will the outbursts level off, or continue ramping up? Fresh observations arrive weekly, packed with twists. This isn't your standard, clockwork comet. It's a live spectacle playing out before us. Part 4. Its origins? Every celestial body, the path of an object hurtling through space, reveals its history. Its destination hints at its origins, and the course of Comet 3I/Atlas weaves a narrative stretching across billions of years and vast distances measured in thousands of light years. This path forms a hyperbola, the scientific label for an unbound arc that veers away without circling back. Comet 3I/Atlas originated beyond our solar system, arced past the sun, and will soon depart forever. With an eccentricity exceeding 1, it's untethered, an independent traveler, merely visiting. Scientists backtracked its route by examining prediscovery photos. Prediscovery refers to scouring archived telescope data for sightings of something before its significance dawned on anyone. It turns out that 3I/Atlas appeared in numerous automated survey shots. Certain captures date to when the comet lingered at 6. For astronomical units from the sun, approaching steadily, chilly, and remote. By piecing these snapshots together, experts refined its orbital path with greater accuracy. That path leads outward, toward the broader Milky Way, yet it points to a specific region. By integrating orbital simulations with observations from the Gaia spacecraft, which charts the locations and velocities of billions of stars, astronomers can speculate informedly on 3I/Atlas's possible birthplace. The conclusion astounds. Our galaxy isn't chaotic, stars cluster in patterns. The majority, our sun included, reside in the slim disk, a broad, mostly level layer of comparatively young, metal-abundant stars circling the galactic core. However, a thicker disk exists too, harboring ancient stars on slanted, elongated orbits. These older stars bulge vertically, extending higher and lower from the disk's plane, and differ in makeup. They arose sooner in the galaxy's evolution, amid scarcer heavy elements. Their metallicity is reduced. The comet's track implies it may hail from this thick disk realm. Should that hold, and if 3I/Atlas coalesced amid those primordial stars, it could predate our solar system. The latter clocks in at 4.6 billion years. Thick disk stars often exceed 7 billion years. Thus, 3I/Atlas might bear frozen remnants and minerals from an era predating the sun's formation. Consider the chemical implications. The nebula that birthed a thick disk star 7 billion years back contained fewer heavy atoms than the one spawning our sun. Over eons, stellar blasts from supernovae gradually infused the cosmos with elements beyond helium. Initial star batches consisted nearly of hydrogen and helium alone. Subsequent ones, like ours, incorporate a modest fraction of heavier stuff. Thick disk stars fall in between, with moderate heavy element traces, but less than in our vicinity. If 3I/Atlas emerged there, its makeup would mirror that diminished metallicity, sparser iron, magnesium, silicon, and other planet-building basics. Yet ample light volatiles would persist. Carbon, nitrogen, oxygen, bound in frosts and compounds. Perhaps that's the reason for the elevated carbon dioxide relative to water we've detected. Perhaps it explains the odd metal proportions. Perhaps this comet serves as a preserved snapshot of chemistry from a less mature galaxy, when the element table felt more sparse. Naturally, certainty eludes us. Retracing an object's journey over billions of years amid galactic dynamics proves challenging. Tugs from nearby stars, brushes with spiral arms, all obscure the path. Still, the mere possibility that 3I/Atlas outlives our solar system is remarkable. We could be gazing at a remnant, an enduring artifact, a vessel from the galaxy's youth. And should we locate its natal cluster, the stellar batch born from identical nebula, we might one day spot relatives, fellow comets, or perhaps rogue worlds, now dispersed galaxy-wide, expelled from the same cradle. 3I/Atlas could represent a fragment of a vast, light-year-spanning inscription, and humanity is only beginning to decipher it. Part 5. What accompanies it on this voyage? Comets transcend mere frozen debris and stone. They act as vessels hauling the biochemical ledger of their genesis. And 3I/Atlas transports an oddly intriguing payload. We've noted the 40 kilograms per second of water vaporizing into the void at ranges where such outgassing ought to remain dormant. That water, or more precisely, the hydroxyl scraps lingering after solar rays dismantle it, first signaled this comet's peculiarities. But water merely opens the tail. Carbon dioxide delivers the jolt. Data indicate 3I/Atlas boasts an unusually elevated carbon dioxide to water proportion. Among solar system comets, water typically reigns supreme as the chief gas, fueling most outbursts. Carbon dioxide plays a role, certainly, but as a secondary force. 3I/Atlas inverts this dynamic. Certain readings propose that 95% of the gaseous outflows from this comet consist mainly of carbon dioxide, with water making up just a small fraction. That's the opposite of what we're used to. It's completely reversed. Nothing like the patterns we observe in our own solar system. What could explain such a high concentration of CO2 in a comet? One explanation might involve the conditions during its formation. CO2 ice forms at warmer temperatures compared to water ice. If 2I/Borisov originated in a hotter zone of its protoplanetary disk, nearer to its host star, it could have trapped more carbon dioxide while shedding much of its water content. Alternatively, the radiation from its parent star might have altered the ices in unique ways that our sun doesn't. Or perhaps the gas giants in that system, if any existed, shifted positions differently, disrupting the disk and blending materials in surprising fashions. Then we have the cyanide. CN, or hydrogen cyanide, shows up frequently in comets and is responsible for the greenish tint many display. Yet in 2I/Borisov, the cyanide emerged later than the water, further along in the heating process. In typical comets from our neighborhood, both appear roughly simultaneously due to their comparable evaporation points. This lag in 2I/Borisov's cyanide hints at some form of isolation. It could be embedded within organic compounds requiring additional heat to release, or perhaps locked away in strata below the surface water ice. Don't forget the nickel, either, that atomic nickel emitting a green glow, detached from its common companion, iron. We've delved into that puzzle before, but it's still noteworthy. Each detected element or compound serves as a hint. The volatiles reveal insights into the heat and pressure at birth. Durable solids speak to the order of solidification and heat treatments. The balance between gases and grains informs us about the object's makeup and its tendency to fragment. Now, onto the big question lurking here, the notion of panspermia. The concept that life, or its essential ingredients, could hitch a ride across the cosmos via comets and asteroids. 2I/Borisov contains water, organic stuff, and cyanide, a vital player in the chemistry leading to life. If you were crafting a comet to deliver intriguing compounds to a world, these would be the precise components you'd choose. But let's stress this, it's all conjecture. No signs indicate 2I/Borisov transports actual life. No proof exists that any comet has ever done so. Panspermia remains fascinating and theoretically feasible, yet unverified, with major hurdles. Space radiation is relentless. Across eons in the void between stars, energetic particles shred intricate molecules. Stellar UV rays wreak similar havoc. DNA, proteins, and even basic amino acids might disintegrate. For any life to endure such a voyage, it'd have to hide deep within the comet, shielded by thick layers of ice and stone. Simpler building blocks, however, could persist, not viable organisms, but molecular remnants. These might have formed in the comet's home system, say in a planetary air or on its surface, before getting folded into the body. Stable and safeguarded enough, they could weather the trip. Analyzing them might unlock secrets otherwise out of reach. The air's makeup from a distant planet, biochemical routes from a long-gone ecosystem, or even coded signals in carbon, nitrogen, and oxygen, ready for interpretation. That's why certain researchers fantasize about chasing down these wanderers from afar, not merely watching from our planet, but launching a probe to rendezvous, touch down, bore in, collect bits, and study them up close. The engineering feats demanded are staggering. These intruders zip by at speeds of tens of kilometers per second. Snagging one calls for a craft pre-positioned or able to ramp up to insane velocities. Yet the rewards for science would be beyond measure. A specimen from foreign stars, reactions from a remote galactic spot, responses to queries we're only starting to frame. 2I/Borisov has already sped billions of kilometers beyond our inner realms. We missed our shot this round, but it's teasing the potential. It's unveiling the wider universe and stoking our appetite for discovery. Part 6. Everyday enthusiasts spotting phantoms. Often, the biggest breakthroughs stem from viewing the information through a fresh lens. Not via code or AI, but through keen human sight and gut feel. And occasionally, that observer isn't an elite stargazer. Allow me to introduce odd radio circles, or ORCs. If they're new to you, that's understandable. They surfaced only in 2019, which feels cutting-edge in cosmic studies. ORCs are enormous ring-shaped features detectable solely in radio waves. They evade visible light. They dodge infrared. Train a radio dish on the proper sky sector, and voila, flawless loops of radio signals. Occasionally, these vast structures stretch across hundreds of thousands of light years, drifting through the cosmos like ethereal halos of interstellar mist. Their true nature remains a puzzle. The prevailing hypothesis points to outflows from galaxies or ripples caused by enormous black holes, yet we're far from certain. They truly baffle us, and spotting them proves challenging since they're dim and merge seamlessly with the ambient radio emissions. Computer-driven search tools often overlook them, as they're programmed to detect compact points or standard features, rather than sprawling, hazy loops. That's where Radio at Home steps in, a crowdsourced initiative that enlists everyday people to scan radio sky images for outliers. Participants aren't hunting for predefined targets. They're on the lookout for the bizarre. Come March 2025, one enthusiast highlighted a remarkable anomaly. Dubbed J131346. 9+500320. It's no thrill in naming, but its essence captivates far more. Two radio loops crossing paths overhead, forming an 8-like silhouette. This marks the farthest and most intense such oddity uncovered to date. And it surfaced not through software, not via expert-led scans, but thanks to a dedicated individual's effort poring over the visuals. The find drew from broadband radio images at low frequencies courtesy of Lofer, Europe's extensive array of radio dishes. Lofer churns out massive datasets, overwhelming for astronomers to review manually. Routine automated systems sift through the bulk, highlighting potentials by criteria like intensity, form, and more. Yet those systems impose cutoffs and biases. They're tuned for the predictable, not the surprises. Here, the human knack for pattern detection shines. Our minds excel at picking out misfits, discerning order amid chaos, and zeroing in on curiosities even without clear reasons. The contributor who spotted J131346, 9+500320 didn't require deep knowledge of these phenomena's mechanics. They simply eyed the picture and sensed something off, and spot on they were. But this isn't an isolated hit. Radio at Home has uncovered several irregularities. One participant identified a colossal radio galaxy encircled by an unusual loop. Another detected a circle at a jet's tip, a trait unforeseen by simulations. These gems might have vanished in the data torrent without human oversight. The takeaway resonates beyond radio studies. We're stepping into a flood of information. Once operational, the Vera C. Rubin Observatory will produce 15 terabytes nightly for a decade. No crew could comb it all. No algorithms will nab every quirk. The solution lies in synergy, tech for the routine grind, people for the unconventional outliers that defy norms. Tying this to Oumuamua, could a hobbyist have caught its peculiarities sooner? Might a data reviewer have picked up the nickel-lacking iron clue ahead of the pros? Could a watcher of comet tails have questioned, Why is it stirring up so distant from Sol? Possibly, or perhaps not. Yet the core idea holds. Oddballs like Oumuamua thrive on broad scrutiny. Experts bring skills, education, and frameworks, but also preconceptions, agendas to validate, and tight schedules. Volunteers offer unbiased gazes, unbound by conventions, ready to observe reality as it unfolds. Tales abound of non-pros unearthing supernovae, asteroids, or fluctuating stars. The Japanese hobbyist Kawao nabbed several comets amid a supernova hunt. Britain's Andrew Gray shared credit for a bizarre star flare. These aren't rarities. They illustrate the power of enthusiastic observers armed with scopes or datasets scrutinizing the heavens. Looking ahead, with observatories deluging us in petabytes, citizen explorers could serve as initial spotters of celestial enigmas, the ones to tag the upcoming rogue comet, the next peculiar radio formation, the latest inexplicable wonder. Pros would then dive deeper, probe, and unravel the science. It's teamwork, and as with any solid alliance, it outperforms solo efforts. Part 7. Citizen Science Against Expert Exclusivity. Yet let's not sugarcoat the friction. Authentic challenges exist. Welcoming public input invites bogus alerts, earnest novices mistaking glitches or static for signals, or fringe believers spotting extraterrestrials in every hiccup, and astronomers rightly fret over it. The Royal Astronomical Society and similar groups have. We've delved deeply into this debate. On the positive side, involving everyday people in science helps clear out the mounting data queues. It enables initiatives to sift through volumes of information that would otherwise overwhelm dedicated teams. Plus, it draws in the general public, sparking real passion for scientific pursuits. Yet, ensuring accuracy remains crucial. A potential find doesn't count until it's thoroughly checked, validated against other sources, and scrutinized by experts in the field. That process demands both time and specialized knowledge. Erroneous alerts pose a significant risk. An individual might highlight something as odd, prompting astronomers to devote days or even weeks to investigation, only to conclude it's merely equipment glitch, a passing satellite streak, or a stray cosmic particle. Such efforts divert resources from actual breakthroughs. When these mistakes accumulate, professionals grow wary of volunteer inputs. The balance between useful signals and irrelevant noise worsens. Weariness creeps in. Another concern is selective perception. Folks hunting for particular features often spot them where none exist. Even experts fall into this trap, but their education and collaborative reviews serve as safeguards. Hobbyists may lack those safeguards, potentially spotting designs in mere chance fluctuations and persuading themselves of their validity. This explains reports of extraterrestrial megastructures encircling Tabby's star or hidden signals in pulsar rhythm variations. Handling instrument adjustments and error ranges presents further hurdles. Seasoned stargazers understand how to gauge observational inaccuracies. They can distinguish a meaningful signal from mere statistical fluke. Novices might not. They could announce a sighting that's simply a minor deviation, irrelevant in broader data analysis. Resource limitations add to the mix. Should a public participation effort gain massive traction, with crowds tagging countless items, the astronomers assigned to verify them could face overload. They simply can't examine it all. Choices must be made on what to pursue first. Consequently, true anomalies might slip through, lost amid the flood. That said, these issues aren't impossible to overcome. They're obstacles, not dead ends. Educational guidelines make a difference. By instructing volunteers on evaluating data reliability, spotting false signals, and gauging potential errors, the incidence of bogus alerts decreases. Guidance systems, pairing seasoned participants with beginners, uphold quality levels. Layered screening, requiring several unrelated contributors to identify the identical feature before escalating it to experts, weeds out unreliable flags. Meanwhile, the benefits are vast. Leveraging collective input for spotting outliers lets you comb through expansive archives more effectively. Input from numerous observers cuts the odds of overlooking a legitimate oddity due to someone's momentary lapse. Varied viewpoints from diverse groups can reveal subtleties that narrow-focused pros might ignore. Tying this to 3i/Atlas, might an amateur observer have caught its nickel irregularity sooner? The spectrum readings were openly available. With appropriate tools, anyone could access and examine them. However, spectral analysis is complex. It involves grasping emission lines, adjusting for wavelengths, and judging data clarity. It's far from a leisurely task. Still, through proper instruction, support, and collaborative networks, a sharp-eyed participant might have detected the peculiarity ahead of media buzz. The same principle applies to its water output levels. Brightness profiles for comets, tracking luminosity changes, frequently come from enthusiast contributions. Had those enthusiasts reviewed ultraviolet observations from Swift and learned to identify atypical behaviors, they could have highlighted 3I/Atlas's accelerated glow-up. They might have noted, this comet's acting strangely, prior to official confirmations. History shows citizen-driven finds deliver results. The transit technique for exoplanets, spotting worlds via slight starlight dimming during orbital crossings, has progressed thanks to volunteers poring over Kepler archives. Efforts like Planet Hunters have yielded several validated alien worlds. Enthusiast asteroid spotters have uncovered Earth-approaching rocks overlooked by formal scans. Backyard supernova seekers often outpace pros in detecting star flares, scanning skies nightly with modest gear, while big observatories book time far ahead. The takeaway isn't swapping out experts for hobbyists. That's ridiculous. Rather, it's clear we require a blend. Pros bring profound insight, conceptual models, and strict verification. Citizens offer wide-ranging scans, novel angles, and unmatched manpower. This isn't rivalry, it's collaboration. In today's flood of information, such teamwork is indispensable. Part 8. The Alignment Phenomenon. October 2025 delivered an intriguing twist. Prime observation windows for both Mercury and Ceres. Mercury, the closest world to the Sun, arced into a stunning evening star gleamed vividly, positioned high in the post-sunset sky. Ceres, the biggest body in the asteroid belt, hit opposition, right across from the Sun in the heavens, shining at peak brightness and nearest to our planet. Online, folks began linking things up. Mercury in view, Ceres on display, and then this odd interstellar visitor, 2I/Borisov, seeming almost animated. Could they tie together? Was a grand celestial lineup unfolding? Might the Sun's gravitational forces be sparking or boosting the comet's outbursts? Straight up, nope. No links exist. Mercury's path doesn't affect an interstellar comet's vapor release. Ceres' spot relative to us won't impact reactions occurring light-years distant. These are separate occurrences, just happening to show up simultaneously. End of story. Yet humans adore spotting designs. It's built into us. Spotting them helps survival. Early folks who linked specific fruits to illness or beast prints to food sources outlasted the oblivious. Thus, our minds are tuned razor-sharp for patterns. Occasionally, to the extreme of inventing them out of thin air. This amounts to pareidolia writ large across the stars. Pareidolia means spotting faces in fluffy clouds or voices in white noise. It's our pattern-spotting instinct run amok, and it crops up constantly with sky phenomena. Old civilizations read signs in planet clusters. A comet streaking amid warfare spelled divine wrath. Planets huddling in one sky sector foretold royal arrivals or passings. The year 1910 offers a spot-on past example. That's when Halley's Comet swung back, looping through the Sun's inner realm on its 76-year cycle. Panic gripped the public. Scientists spotted cyanogen, a deadly gas, in its tail. Tabloids blared alarmist stories. Comet's toxic sweep will engulf Earth. Folks snapped up gas masks. Others taped shut their homes. There were tales of self-harm from those certain doom was coming. Naturally, zilch occurred. The tale's material spreads out thinly. It's practically empty space by our world's measure. Any cyanogen hitting us was tiny, untraceable. The comet brought zero danger, yet its timing alongside unrelated happenings, like sun flares, social turmoil, quakes, stoked the fear. People drew lines between unlinked points. The current buzz around 2I/Borisov echoes that. The comet's quirks are real oddities. With Mercury and Ceres visible concurrently, narratives spring up fast. Perhaps solar vibes are rousing it. Or maybe pulls from gravity are nudging its course. Or this could hint at a bigger puzzle unsolved. Experts crunch the data. Mercury's tug on something in the far solar fringes? Basically no. It's a speck, just a tad bigger than Luna, and worlds away. Ceres is tinier, impact even feebler. Even all the planet's collective gravity couldn't meaningfully tweak 2I/Borisov's actions from where we watch. The comet acts from its core mechanisms, sun heat, and makeup, not Mercury's orbital spot. Still, when tales captivate more than truth, facts take a back seat. Our psyche hungers for tales. Tide events suggest purpose. Loose ones seem haphazard, disordered, pointless. Linking the comet's flares to planet spots implies structure, foresight, significance. Without ties, the cosmos feels like a place where weirdness strikes at random, and that's mentally jarring. This gets worse with confirmation bias. Once hunting ties, they pop up all over. Mercury shown during an earlier comet find. Ceres neared opposition for another bizarre sighting. Ignore that Mercury appears often yearly. Ceres opposes annually. Dismiss that rare sky finds occur nonstop. The mind skips mismatches, clings to fits. Social platforms supercharge it. Back then, a wild idea on planet-comet ties might earn eye rolls from pals, dropping it. Today, share it digitally, and boom, a like-minded crowd assembles. Swap pics, graphs, proofs of setups. One adds fuel, another spreads it. Soon, a rival story challenges the real science. The takeaway isn't that folks are dim or easily fooled. The takeaway here is that coincidences pack a punch, and our minds struggle to brush them off. From a stats perspective, amid countless celestial occurrences unfolding constantly, a few are bound to overlap by sheer luck. Yet those overlaps strike us as profound, even if they're meaningless. This dynamic plays a key role in how folks make sense of oddities such as the three-eyed Atlas alignment. When you're tuned to spot interstellar plots or convinced that celestial lineups hold significance, the comet's bizarre path turns into proof of a bigger scheme. Perhaps it's no ordinary comet. Perhaps it's man-made. Perhaps it's reacting to transmissions from nearby worlds. Perhaps it's a cog in some vast, enigmatic cosmic system. And this leads straight into a weirder twist in the tale. The engine driving deceptions, wild speculations, and the way people morph scientific enigmas into enduring folklore. Part 9. October 2025. Update. Did the event unfold at all? October 8, 2025. Blue Origin's INS-36 flight. A crew of 6, lasting 11 minutes. One enigmatic traveler whose identity remained hidden right up until touchdown. The spacecraft rocketed upward, breached the Kármán line, drifted in zero-G conditions, eased back with parachutes, and settled into the Texas scrubland. A triumph. Yet another seamless outing for their orbital tourism venture. Their 15th suborbital jaunt. Business as usual. Or nearly so. That's the narrative on record. ABC News reported it. Medium published an article. A smattering of aerospace reporters posted updates on Twitter. The anonymous rider's name emerged only after the craft landed. An everyday civilian who sought discretion during the ascent but welcomed the spotlight later. Nothing out of the ordinary. Folks shell out for seclusion routinely. But the odd part lingers. It's what nags at dedicated space enthusiasts. The quiet. An unsettling, near-claustrophobic dearth of buzz. No clips exploding online. No hot topics trending. No star-studded responses, jokes, or quick video dissections on TikTok. A voyage beyond Earth. A private team venturing to space's frontier. The sort of feat that, not long back, would have dominated headlines for a week. It scarcely caused a ripple. Pause and consider it. 6 souls departed our world. They savored the thrill of floating free, gazed at Earth's arc silhouetted against the void, and made it home intact. Remarkable stuff. It ought to feel remarkable. Yet the web just yawned. Platforms scrolled past in mere hours. The account evaporated like mist. What's behind it? Why the scant records? Blue Origin typically shares interior clips. Stunning visuals of riders tumbling playfully, grinning, peering out portals. Where were such glimpses? Why didn't they flood media outlets? Why didn't unmasking the secret flyer spark intrigue? Who was this person? What prompted the veil of secrecy? These spark typical chatter, the fuel for prolonged debates and fascination. But zilch. Total hush. As though the trip occurred not merely in space's void, but in a bubble devoid of scrutiny. And that void, that emptiness, morphs into a presence of its own. The quiet amplifies beyond any press release. Doubts creep in. Tough queries arise. Was the mission truly as portrayed? Did Six actually board, or did the roster differ? Was the hidden traveler genuine, or a ploy to sidestep pre-launch hype? Did the pod blast off precisely on October 8th, or was old video reused with a fresh timestamp? These notions veer into suspicion, plot-hunting logic that spots phantoms in every corner and doubts all. Yet occasionally, the void of proof carries weight. When an event warrants fanfare and stays mute, probing the cause becomes essential. Compare it to April 2025, merely 6 months prior, when Blue Origin fired off a different New Shepard trip, and that one burst into collective awareness. Not due to a glitch, but courtesy of the writers. Katy Perry, Gayle King, the inaugural all-women lineup, big-name figures boasting massive audiences, the precise setup for splashy coverage, which it got, though hardly the spin Blue Origin hoped for. Shortly after the broadcast wrapped, online forums ignited with plot claims. Viewers insisted the whole thing was staged. They scrutinized each second of video for flaws. How hair shifted in weightless air turned into a debate arena. Did it billow authentically? Did it seem overly rigid? Real strands, a hairpiece, or digital trick? The pod's entryway drew fresh scrutiny. One observer alleged it unsealed unlike prior runs. They shared juxtaposed clips, added pointers, highlighted purported irregularities. Wasn't the mechanism positioned oppositely before? Hadn't the panel swung the other way? Why the variance? Then the outlandish theories piled on. Assertions of chroma key setups, charges that the crew was shot in a soundstage with bogus views displaying looped planetary shots, claims that the limbs appeared resembling the flawless grip of a store dummy, overly sleek and synthetic. Gripes surfaced over the lack of clear burn traces on the spacecraft following its return through the atmosphere. Each minor aspect turned into proof of trickery. Reporters systematically dismantled the assertions. Strands of hair act strangely under zero gravity since nothing tugs them downward, letting them react to breezes, electric charges, or unpredictable shifts. The door system stays consistent over multiple voyages. Variations in filming positions and illumination alter the appearance. Glints on face shields warp the view. Burn indicators might not show up based on how much soil from the touchdown area obscures them and the sharpness of the footage. Yet, refuting the ideas didn't halt the speculation. In fact, it only intensified it. Folks determined to view the journey as staged saw the refutations as part of a larger concealment effort. They probed further, uncovered additional clues, and crafted intricate scenarios detailing the supposed fraud's execution. The notion of a plot turned into something that perpetuated itself. Today, we've seen a pair of voyages, duplicate expeditions, identical booster, similar overall design, separated by half a year. The initial one sparked a blaze of scrutiny and skepticism. The follow-up hardly registered any buzz. So, one can't help but wonder, which raises more red flags. Part 10. Cosmic Enigmas as Reflections. The cosmos continues to hurl surprises our way. Items that puzzle us, transmissions that baffle, occurrences that challenge our well-built theories. And invariably, each instance prompts us to react in twin ways. Initially, we rush to grasp the underlying principles. Then, we overlay our own experiences onto the unknown. Consider Oumuamua, detected in 2017. The inaugural verified visitor from beyond our solar system, spinning erratically, with a ruddy hue, stretched form, and a subtle but detectable speed-up as it departed. That boost didn't align with a simple pull from gravity alone. An external force seemed to propel it. Experts suggested venting gases. Despite no direct sightings of fumes, it could have been emitting trace amounts of evaporating substances, mimicking a faint comet's push. Alternatively, perhaps a block of solid hydrogen, ICH2, sublimating without notice. Or it might have been debris from a broken world. Its form and rotation generating pushes from light radiation. However, a group of individuals, among them certain researchers, floated another idea. Suppose Oumuamua was man-made? A photon sail, a stellar sail, a delicate layer of fabric driven by sunlight. Such a setup could account for the speed-up. And if engineered, it might represent a scout from a distant culture. Perhaps scouting, or possibly abandoned, wreckage from an extinct extraterrestrial realm. A parallel scenario unfolded with Tabby's star, KIC 846-2852, a celestial body in the Kepler survey displaying peculiar fades in luminosity, sharp and uneven drops, occasionally plunging by 22% or greater. Nothing planetary could cause that. No world spans wide enough to eclipse so much glow. Plus, the fades lack the steady rhythm of a world crossing its path. Stargazers floated ideas like hazy veils, clusters of icy wanderers, or rubble from a world-smashing event. But one study, somewhat in jest, floated the notion of an extraterrestrial superbuild, a Dyson array. Countless energy-capturing arrays or dwellings circling the sun, harvesting its power while intermittently shading it as they shifted. It matched the observations, more or less. Peculiar radio rings, quick radio pulses, 3I/Atlas. Each puzzle serves as a canvas for our dreams and dreads. Are we solitary? Does the cosmos ignore us or act with purpose? Do companions exist elsewhere? And if they do they mirror us or defy all understanding? The mental dynamics at play are profound. Pareidolia, spotting designs in chaos, factors in heavily. We spot visages in vapors, detect murmurs and static, and attribute smarts to stellar oddities. It's no folly. It's how our minds function. We're wired for spotting motifs, and we lean toward overinterpreting. Safer to read threat in a silhouette than overlook danger as mere shade. There's also a deep yearning for connection. We crave encounter. We yearn to affirm we're not isolated flickers of awareness in an immense, frigid void. Every irregularity offers potential, a glimmer, an entry that could reveal marvels. Thus, we press against those entries with fervor. 3I/Atlas acts as a looking glass. Within its radiant emerald tail, we glimpse our innate inquisitiveness, our thirst for purpose, our wish that reality holds greater oddities and delights than we suppose. And perhaps it does. Perhaps someday we'll encounter the truly baffling. A discovery demanding we overhaul our laws of nature or concede company in the stars. But that moment remains distant. For the present, it's merely an icy wanderer. An unusual one, a captivating one, yet likely just that, an icy wanderer. And that's sufficient, for even ordinary wonders hold magic. Part 11. The repository of extraterrestrial setups. Picture the Milky Way as a vast repository, not of tomes, but of relics. Wanderers like comets and rocks, plus wayward worlds hurled out amid the turbulent birth of solar families and cast into the void between stars. Every relic serves as a sealed dispatch, bearing clues from its birth system's past. And now and then, one such dispatch drifts its washing up on our doorstep. That's the essence of interstellar visitors. They're like messages from distant star systems, not implying smart aliens, but just outsiders, unfamiliar, shaped by environments nothing like our own solar neighborhood. Each one we spot is a lone clue, a single snapshot. Gather enough of them, and we begin grasping the wild variety in how planetary setups brew their chemical soups. Comets from our solar system are pretty consistent. They all originated in the same swirling nursery disk, drawing from the same blended cloud of gas and grit, bathed in identical starlight. They differ a bit, of course. A few pack more carbon monoxide, others lean heavier on water, based on their birthplace in the disk and the heat they endured. But their kin, relatives at closest, brothers, sisters, maybe distant kin. Interstellar ones? Total outsiders. They coalesced around other suns, in disks with unique makeups, varying temps, and chaotic orbits, all their own. And so far, every single one we've caught sight of stands apart. Oumuamua. Arid, not venting gases, with a bizarre form and some unexplained speed-up. It didn't resemble our comets. It didn't behave like them either. If it qualified as a comet, it was a breed we'd never met. 2I/Borisov, loaded with carbon monoxide. It showed standard comet antics, yet its gas-to-dust balance hinted at a chillier birthplace than what our locals usually get. It felt somewhat recognizable, yet curiously skewed, akin to a regional twist on your native tongue. 3I/Atlas, spewing water and CO2 from afar, nickel sans iron, cyanide popping up delayed. None of its actions match what we know. It's chatting in a tongue we're only starting to parse. Three visitors, three utterly distinct chemical profiles. Project that forward. Figure these three mirror the bigger crowd, and the galaxy's comet variety explodes into view. Not every star family churns out our style of comets. Actually, perhaps the majority skip that recipe. Ponder the implications. Certain systems could favor nitrogen frost comets, echoing Pluto's crust. Elsewhere, methane might rule as the key gas. Around heftier stars, the frost line, where water freezes solid, sits way farther out. Comets there might brew in icier zones, hauling altered volatile blends. In setups with wandering gas giants, the disk churns up, blending stuff from hot and cold bands, yielding comets with oddball mashup recipes. Might some tote compounds we've never dreamed of? Stuff that's chemically feasible but needs birth processes absent here. Rare organics, peculiar frosts, substances that'd thrill any chemist. The cosmos is vast, after all. The playground of star weights, disk recipes, light baths, and orbital tumults is immense. Evolution pokes every corner of that playground, and some outcomes must be downright weird. Let's push this idea ahead. If biology demands specific starters, water, carbon chains, phosphorus, nitrogen, sulfur, then comets missing those bits are barren. They can't spark life. They can't drop proto-life chems on worlds. Perhaps loads of interstellar comets are duds like that. Maybe Oumuamua was just a dead stone drifting empty space. Yet if even a slice of them packs the needed mix, that slice counts big. Comets roam the stars, after all. They hop between suns, spanning light years. And if they lug organic bits, amino building blocks, or even tucked away hardy bugs, then life seeds could hitchhike galaxy-wide. That's panspermia, the idea that biology hops worlds via roving rocks. It's debated. It's untested, sure, but not out of the question. And 3I/Atlas, with its water flows, organic traces, and cyanide hints, holds the raw stuff. Not alive, likely, but the sparks that might ignite on the right world. Each interstellar find bulks our data set. We've got 3 now. Give it a decade, we could hit scores. Half a century, maybe hundreds. For every one, we'll probe makeup, path, outburst rhythms. We'll forge a data-driven picture of the cosmic lineup. Perhaps we'll learn water-heavy comets abound, that most systems crank them out. Or we might discover our setups the freak, with watery ones scarce and dry, carbon-loaded types the norm. Both revelations would captivate. And who knows, we could snag a comet screaming biology. Tough-to-fake signs like phospholipids, intricate carbons with hand-deadness, isotope quirks yelling alive. That'd upend everything. Proof of life beyond. Proof chemistry's not Earth's exclusive. We lack that jackpot so far. 3I/Atlas doesn't seem to haul passengers. But it does tote knowledge. And knowledge fuels discovery. Each cosmic wanderer that drops by is like a complimentary treat left right at our front door. We just need to peer a bit harder to unwrap it. Part 12. Nickel acts as a harbinger. Let's circle back to that peculiar nickel irregularity, since it's far more than a mere oddity. It's a hint, a molecular marker. And such markers reveal the journey someone's taken. Stars function as cosmic workshops. Deep in their hearts, nuclear fusion transforms hydrogen and helium into denser substances. Carbon, nitrogen, oxygen, silicon, sulfur, iron. When enormous stars detonate in supernovae, the eruption forges even weightier atoms, nickel among them. These particles disperse across the void, blending into nebulae, and over time, folding into fresh stars and worlds. Yet stars don't all follow identical formulas. The concentration of dense elements, what experts term metallicity, differs widely. Newly born stars, emerging from clouds laced with remnants from countless prior supernovae, boast elevated metallicity. Ancient stars, sparked to life in the galaxy's infancy with scant supernova contributions, display minimal metallicity. Nickel and iron both emerge from supernovae, though their proportions shift subtly based on the blast's nature. Type I events, involving a white dwarf gobbling up material until it bursts, yield distinct nickel-to-iron balances compared to core-collapse supernovae, where a hefty star caves in on itself. Should 3I/Atlas have originated in a stellar nursery infused with an atypical blend of supernova varieties, its nickel-to-iron proportion could end up lopsided. We suspect 3I Atlas hails from the thick disk, a more mature group of stars. Those in the thick disk generally show subdued overall metallicity, yet the proportions among heavy elements can fluctuate. If the nickel separation evident in 3I Atlas mirrors its progenitor star's makeup, then this comet serves as a guidepost. It sheds light on the galaxy's chemical progression in methods otherwise hard to grasp. Consider this. We can scrutinize stellar atmospheres through spectroscopy. We gauge their iron, nickel, and all the rest. But stars lie at vast distances. We're limited to probing just a small handful in depth. And extinct stars? The ones that burned out eons ago? We can't touch those. Comets from such realms, however, are sealed archives. They lock in the elemental state from their origins. Sampling 3I Atlas up close, probing its isotopes, minor elements, crystalline forms, would let us grasp a fragment of a star system potentially billions of years old and thousands of light years distant. We'd be deciphering chronicles etched in atomic script. Now, indulge a bold notion, an offbeat concept that circulates in niche discussions. Might odd metal patterns, like elevated nickel, signal tampered substances? Not the usual alterations from heat or pressure, but engineered ones. Suppose a sophisticated society were excavating asteroids, purifying ores, erecting orbital frameworks. They'd produce refuse, dross, debris, emissions. Such stuff would exhibit quirky elemental mixes, as manufacturing favors certain components. Perhaps they'd harvest iron for building and toss the nickel-laden scraps, or deploy nickel for targeted uses and jettison the surplus. A comet coalescing in a rubble ring laced with such industrial byproducts could absorb those quirky metals. Then, after eons or more, it gets flung out, drifts through the galaxy, and enters our solar system. We spot the nickel quirk and puzzle over it. To state it plainly, zero proof exists that 3I Atlas is manufactured or bears tech imprints. Zilch. This remains pure conjecture, bordering on sci-fi. The vast majority of researchers reject it flat out, though it's not ruled out by physics. Without a straightforward natural account for the nickel separation, even outlandish theories warrant consideration. The probable cause lies in everyday geochemistry, nickel-bound in metal-organic setups, separation amid cooling phases. Or some mechanism we haven't pinpointed, one routine in alien systems, but scarce or missing here. What thrills me, though, is this. Every comet bears an elemental code, a tag encoded in atoms and variants. By assembling a collection of these codes, by inventorying the makeup of scores or hundreds of interstellar travelers, we could chart the galaxy anew. We'd link chemical profiles to paths traveled. A comet approaching from the galactic core's vicinity might reveal distinct abundances versus one from the distant fringe. One from the thick disk could reveal markers tied to antiquity. We'd employ comets as scouts for the galaxy's architecture and development. Picture a time when interstellar arrivals are routine, our sensors so sharp we're logging them by the score annually. Spectroscopic scans for each. Backward tracing of orbits to their limits. Compositional data fed into the archive. In time, trends surface. We discover that comets originating from certain galactic zones tend to be rich in carbon. Those from other areas carry more water. And we're beginning to grasp the reasons behind this pattern. Perhaps carbon-heavy zones birthed more low-mass stars, leading to distinct chemical makeups in their surrounding disks. Or water-abundant areas might have experienced heightened supernova blasts, infusing the clouds with extra oxygen. 3I Atlas marks the initial chapter in this cosmic catalog. Just a single record, a lone piece of data, yet it lays the groundwork. Meanwhile, that odd, isolated nickel stands as a testament that each finding carries its own narrative. Every elemental balance offers a hint. With patience and precision, we can decipher these tales and reconstruct the galaxy's evolutionary saga. Part 13. The Hidden Crowd. 3 visitors in total. 1I/Imamua, 2I/Borisov, and now 3I/Atlas. 3 verified interstellar travelers over just 7 years. Not a huge tally, but sufficient for basic stats, enough to gauge how many others slip by unseen. Experts have crunched the figures using spotting frequencies, observation scopes, and traits from these trio. Their calculations indicate that right now, Several such intruders likely lurk inside Jupiter's path. Tiny, shadowy, zipping along swiftly, beyond the reach of typical scopes. We've nabbed 3 thanks to sheer fortune, because they neared our planet, glowed sufficiently, or showed up in prime sky spots during optimal telescope sessions. How many evade us? Scores? Hundreds? For each interstellar comet we snag, likely dozens glide past without a trace. A few are too dim. Others streak by too quickly for proper tracking. Some pop up in overlooked sky regions. Spotting them proves tricky, though advancements are streamlining it. Fresh monitoring programs are launching with superior sharpness and broad sweeps. The Vera Rubin Observatory, rising in Chile, will sweep the full-night sky every couple of evenings, capturing details to extreme dimness levels. It'll pick out asteroids, comets, blasts from dying stars, any shifts or motions, and interstellar drifters too. Projections say Rubin might uncover one such object monthly, possibly exceeding that. That's at least a dozen annually. Over 10 years, we'd amass more than 100 verified interstellar guests. Now that's a solid data set. Enough to form solid insights on makeups, birthplaces, and overall numbers. The Square Kilometre Array, a radio setup spanning Australia and South Africa, will lend a hand as well. Radio scans can pick up gas releases from comets, including the subtle ones. SKA may flag interstellar comets that visible light gear overlooks. Orbiting UV and IR scopes will nab active comets hidden from optical views. Each emerging tool boosts our knack for detecting these dim, speedy nomads. Yet finding them is merely step 1. Probing them deeply is the real hurdle. Interstellar arrivals barrel through at speeds of tens of kilometers per second against the sun. By the time we detect them, plot their paths, and schedule deeper looks, they're frequently outbound. Oumuamua was already departing when we found it. We managed a single solid observation before it dimmed away, too remote for further study. With 2I/Borisov, we intercepted it on approach, granting months for examination. Global scopes trained on it. We gathered spectral data, brightness patterns, and depth records. That's the dream setup. 3I/Atlas we also nabbed fairly soon after entry. We're pulling in quality info, but it'll soon hit its solar closest point, loop around the sun, and vanish back to the void. And poof, it's lost for good, barring a deliberate chase. Ideas are floating for pursuit craft aimed at interstellar targets. Probes built for rapid liftoff, intense thrust, and rendezvous with a visitor while it's still cruising our system's core. The hurdles are massive. You'd require a vessel prepped and waiting, set to blast off at a moment's notice. Potent engines to sync with the target's pace. Plus gear to dissect makeup, form, perhaps snag samples. But the rewards? Monumental. Picture touching down on an interstellar comet, burrowing into its crust, harvesting frozen water and stone from a foreign stellar realm, hauling it home for lab dissection. The discoveries from such loot would stretch the imagination. We'd nail exact isotope mixes, revealing atomic events in its home star. We'd probe intricate organics impossible to assay from afar. We'd hunt for building blocks of life, like amino acids, or hints of early chemistry. Heck, even ancient microbial traces if fortune smiles wildly. Life or not, we'd unlock the fine points of extraterrestrial world building. Each compound, each rock type, each atomic signature, a breadcrumb trail. Researchers are already sketching these ventures. Blueprints are out there. Funding pitches are in motion. This isn't fantasy. It's tough tech, but within reach. In 50 years, perhaps hundreds if we'd ramped up our monitoring efforts, we could have documented scores of objects from beyond our solar system. We might have captured a handful of them. We could have brought back material from several more. Armed with that information, we'd gain a thorough grasp of comet swarms across the galaxy, the variety in planetary setups, and perhaps even how widespread the ingredients for life are out there. 3E Atlas offers a teaser, a sneak peek at what could be achieved. It demonstrates that these visitors from interstellar space aren't mere oddities. They're routine. They're all around us. And they're packed with insights we're eager to uncover. That hidden horde is drifting out in the void, ready for discovery. We'll track them down, one at a time, examining each closely and assembling the big picture on planetary formation, chemical differences spanning the stars, and who knows, the true frequency of life itself. Part 14. When oddities pile up, timing 00. Fives, time to pull back. Let's consider the wider view. Since 3 Atlas isn't the sole peculiar development in astronomy these days. Far from it. Strange radio loops, enigmatic bands of radio waves. Source unclear. Rapid radio flares. Brief bursts of radio power lasting milliseconds, originating from far-off galaxies. Causes under dispute. Tabby star. Unusual fading behaviors not completely resolved. Oumuamua, the interstellar visitor with unexplained speed-up, 3 Atlas. The comet displaying implausible water output and metallic oddities. And that's merely the spotlight cases. Countless others lurk, lesser anomalies, fleeting occurrences that evade standard labels, spectral signatures that ought not to appear, bodies traveling paths that resist simple interpretation. The field is brimming with puzzles that baffle us. And that's a shift. For much of the 1900s, astronomy suffered from scarcity of observations. You'd aim a scope at a target, snap an image or spectrum, then devote months to dissecting it. Breakthroughs were scarce. Weird findings, scarcer still. When an outlier emerged, it drew fierce examination, with little else vying for focus. Today, we're swamped by information. Robotic scans produce terabytes nightly. Celestial catalogs log billions of items. Detectors for gravitational ripples catch collisions. Radio arrays sweep the heavens nonstop. We're spotting so much that follow-through becomes impossible. And abundance breeds abundance of quirks. Scan a billion targets, and if just one in a million stands out, you've got 1,000 enigmas. Many prove to be equipment flaws, processing errors, labeling mistakes. Yet a few will hold up, and sifting them demands effort. This is an age where curiosities surpass our theories. We're unearthing phenomena quicker than we can account for them. That's thrilling yet risky. Thrilling, as fresh oddities spark novel theories. Pulsars, gamma-ray explosions, gravitational ripples, all began as baffling signals. It's in these puzzles that advances ignite. But risky, too, since buzz can escalate wildly. Each quirk gets touted as a game-changer. Extraterrestrial megastructures, propulsion relics, space-time shortcuts, dark stuff encounters. The press devours it, the audience laps it up. Then, in 9 out of 10 instances, a mundane cause emerges. Obscuring dust, sensor interference, mistaken identities for familiar things. The risk lies in undermining trust. Folks hear possible extraterrestrials repeatedly, followed by merely dust, just as often, and faith in experts wanes. They view science as fanciful guesswork. Or worse, they cling to the exotic idea, accusing researchers of concealment. Tabby star serves as a warning. Once the megastructure idea hit the news, it captivated everyone. Online chatter surged. Stories proliferated. Then deeper looks revealed dimming tide to wavelengths, pointing to dust rather than constructs, sparking pushback. Some embraced the facts. Others decried the experts as mistaken or deceitful. Yet the truth is, Tabby star remains fascinating. The dust theory doesn't cover every detail. Ongoing watches reveal intricate changes. It's an unusual sun, maybe ringed by wreck from a world-shattering impact, or engaging in processes we haven't fully grasped. It's genuine inquiry, worthwhile, simply not from another world. The takeaway: quirks are chances. They compel us to sharpen theories, explore fresh causes, question old ideas. Even sans paradigm shifts, they propel the field forward. Oumuamua's speed up, even if mere venting, compelled experts to revisit low-temp evaporation, unusual frosts, crustal traits. That's advancement. 3 Atlas presents yet another chance. Its water yield questions our grasp of when volatiles kick in. Its nickel peculiarity urges reflection on metals and comets, a topic we've largely overlooked. Our comets often get overlooked since they lack prominent metal signatures. The prevalence of carbon dioxide raises intriguing queries about the environments in protostellar disks elsewhere. Accumulate sufficient irregularities, and trends might start to surface. Perhaps those peculiar radio rings and rapid radio pulses connect in some way, both tied to powerful ejections from galaxy cores. Perhaps wanderers like Oumuamua and 3 Atlas signify separate groups, shaped by unique origins. Perhaps this diverse array of fleeting cosmic events reveals core truths about the universe's underlying vigor. Or perhaps that's a stretch. They could all stand alone as isolated oddities, simply coinciding in our era thanks to our advanced detection tools. Both perspectives offer value. The trick lies in balancing doubt with curiosity. You can thrill over an outlier without insisting it upends established principles. You can explore unconventional ideas without clinging to them rigidly. You can adapt your views as fresh data emerges. Effective science outreach thrives here. In covering 3 Atlas, ethical reporters and researchers ought to note, this comet acts atypically. We're probing various theories. Here's our current understanding. Avoid framing it as alien craft defies natural rules or experts stumped by bizarre entity. Such drama drives traffic, but subtlety rarely does. Measured wording seldom spreads like wildfire. Thus, the sensationalism engine churns ahead, transforming curiosities into supposed breakthroughs, only to breed let down once ordinary causes prevail. The fix isn't halting coverage of outliers. It's embracing openness about unknowns, offering diverse theories, and revising as facts evolve. Engage audiences as capable grown-ups who grasp nuance. They mostly do. Folks get that science unfolds gradually, that evolving insights and admissions of gaps are valid stances. 3 Atlas forms just one piece in this pile of puzzles. It's noteworthy. It's captivating. Yet it doesn't confirm any grand theory yet. It's an observation, an enigma, a chance to gain knowledge. Regardless of whether it proves a quirky organic comet or an unprecedented find, the act of examining it, formulating ideas, debunking notions, sifting evidence, holds real worth. That's the essence of science. And when conducted with integrity, science ranks among humankind's finest triumphs, particularly amid the unknowns it confronts. Part 15. Closing thoughts. Vibrant yet organic. And so we've delved deep into the enigma of 3 Atlas across countless words. An extrastellar comet venting water vapor in regions where it defies expectation. Radiating emerald hues from nickel and cyanide. Flickering intermittently, almost intentionally. Bearing molecular traces from a foreign stellar realm. Potentially from a bygone phase in the Milky Way's evolution. Does it pulse with life? Poetically, perhaps. It's in flux, adapting, interacting with its surroundings. It activates where inactivity seems the norm. Its actions evoke intent, though we recognize they're governed by physical and chemical principles, not agency. But biologically alive? Highly improbable. No signs of vital functions appear. No energy cycles, no replication, no data encoding or exchange. Nothing resembling life's defining traits as we know them. 3 Atlas is essentially an icy boulder, warmed by solar rays, expelling vapors and particles per immutable rules. Still, those rules are yielding a spectacle unlike any prior. Unheard of water evaporation at vast ranges. Nickel absent its iron counterpart. CO2 as the lead player. On-off patterns hinting at intricate innards or rarefied ices. Each sighting deepens the riddle. So what's its nature? The prime candidate remains a conventional comet born in alien circumstances far removed from our sun's neighborhood. It might have coalesced beyond its host star in chillier zones favoring CO2 frost over H2O. Its natal star could have sported atypical elemental mixes, yielding strange metallic balances. Or eons adrift in the void might have reshaped its outer layers through cosmic erosion. The organometallic idea fascinates. Should nickel bind into gaseous forms like nickel carbonyls, it might account for the separate spectral lines. That demands particular formative chemistry, but nothing outlandish, just rare. The thick disk provenance intrigues too. Should 3 Atlas date to 7 billion years back, bearing isotope markers from galactic antiquity, it could clarify the peculiarities. Primordial frosts, archaic reactions, relic minerals, all locked in the interstellar chill and now unveiled as heat stirs them. Might it be engineered? A scout? An abandoned vessel? Some relic of tech? The data argues against it. No aspect of 3 Atlas demands an artificial origin. Everything we observe here can likely be accounted for by ordinary natural mechanisms, or at the very least, they offer plausible explanations. Resorting to extraterrestrial origins feels superfluous. Still, let's play with the idea briefly. Suppose you aim to craft an object capable of enduring a voyage across the stars, and remaining noticeable eons afterward, what approach would you take? You'd likely encase it in something resembling a comet, shielding the core contents with layers of ice and stone. Perhaps you'd embed distinctive chemical traces, signals that would catch the eye of spectral analysts. Allow the object's natural vaporization to expose those clues as it nears a sun. This remains sheer conjecture, devoid of supporting proof. Yet it's intriguing to consider that any engineered voyager from beyond might initially seem unremarkable. It could mimic a comet, an odd one, no doubt, but passable as a product of nature until closer scrutiny reveals otherwise. That's probably the case with 3I/Atlas, most assuredly so. Yet the mere fact that we're pondering this speaks volumes. This comet is peculiar enough to ignite our curiosity, to spark speculation, to compel us to entertain ideas we'd typically brush aside. And perhaps that's the true worth in all this. Not debating if 3I/Atlas is purely natural or somehow constructed. Not quibbling over whether its makeup is just atypical or truly groundbreaking, but how it provokes reflection. It prompts us to challenge our preconceptions. It underscores that the cosmos dwarfs and defies our narrow perspective. Nature has had eons and countless stellar realms to experiment with chemistry, and we've scarcely scratched the surface of its potential. Each wanderer from interstellar space poses a test. It tests our frameworks, our hypotheses, our notions of the ordinary, and such tests drive progress. Oumuamua upended our grasp of cometary behavior. 2I/Borisov questioned our expectations for carbon monoxide levels. 3I/Atlas is appending it all. From volatile compositions and metallic elements to activation ranges and material variations. The path forward is straightforward. Monitor 3I/Atlas closely as it heads toward perihelion. Record it comprehensively. Gather spectra, brightness variations, gas output levels, dust-to-gas proportions. Seek out fresh spectral features. Observe whether iron emerges at last or if the nickel irregularity lingers. Contrast data with simulations. Hone those simulations. Formulate forecasts. Validate them. And gear up for the subsequent interstellar arrival, since more are bound to come. The galaxy teems with these nomads, and our spotting tools improve annually. Every discovery will present fresh enigmas, additional hints, broader insights into planetary development and dynamics amid varied star settings. Someday, we might even capture one. We'd touch down on its surface, bore into it, retrieve specimens. We'd scrutinize its isotopes in Earth-based labs, examine its crystals via electron scopes, probe its organics for life-building compounds, and uncover insights beyond current imagination. For now, we observe, we quantify, we ponder, for that's our essence. We gaze at the heavens and pose inquiries. Why does that comet stir so remotely from its sun? What's its origin? What lessons does it hold? Those inquiries hold merit even sans resolutions. For inquiry launches discovery. 3I/Atlas journeyed from the depths out there, spanning light years and ages, bearing a dispatch etched in water, nickel, and cyanide. We never requested this dispatch. Its meaning eludes us still, but we're attuned. We're vigilant. We're absorbing. And through this pursuit of knowledge, this relentless drive to comprehend, we uncover what's truly vital in this tale. Not the comet itself, but us, inquiring, marveling, extending toward an entity from realms unimaginably remote, striving to decipher a dispatch from alien shores. The cosmos dispatches these missives ceaselessly. Stellar greetings, notes adrift, envoys from the void. With each arrival, we're reacquainted with our dwelling in an immense, timeless, bewilderingly abundant expanse. An expanse that will always surpass our comprehension, always astonish, always proffer novel riddles. 3I/Atlas is but one such riddle, one comet amid boundless skies. Yet it's ours to unravel now. Whether merely in relic of primordial frost or harboring greater intrigue, whether its enigmas unravel swiftly or endure for generations, will persist in our gaze. We'll continue querying. We'll stay receptive to the cosmos's whispers, for that's humanity's core. To behold the anomalous in the nocturnal vault and steadfastly engage. To seek truths amid cosmic reticence. To discover awe in a burst of water vapor at 40 kilograms per second, in the verdant gleam of misplaced nickel, in a path tracing to unattainable stars. We are minuscule, the cosmos immense, but bridging us and that immensity, between our scopes and those far-flung realms amid comets, amid the gap between our inquiries and any responses we could uncover, a dialogue unfolds, a languid exchange stretching across ages and vast cosmic distances, etched in streams of light, emission spectra, and the laws of celestial paths. The third atlas uttered its voice. We caught its message and remained attuned, eager for whatever it would reveal thereafter.